Hi, this is John Whitaker for the Mathematical Analysis 1 class, and this is our 31st video lecture. And today I want to start off with a theorem having to do with continuity, and here's what it says. It says, let E be a non-compact set in R. Okay. Then we're going to have three statements here. First, there exists a continuous function, continuous and bounded. A continuous function on E which is not bounded. B, there exists a continuous and bounded function on E that is not uniform. That has no maximum. Its maximum. And C, if E is bounded, not E, E is bounded, then there exists a continuous function on E which is not uniformly continuous. Which is not uniformly continuous. Okay, so that's the statement. We're ready to start the proof. Okay. There's three parts to prove, and we're going to start off with the assumption that E is a non-compact set in R. Okay. All right. Now we will consider two cases to prove parts A and B of the theorem. Okay. All right, the first case, case 1, well, it will assume that E is not bounded. We'll assume that E is bounded in this case. E is bounded. Okay, so what we're thinking is that E is non-compact. Okay, the only way that you're non-compact in R is either you are unbounded, okay, or you are not closed. One of those two things has to happen. And since E is bounded, that means that E is not closed. So let me write that down. Since E is not compact and is bounded, that means E is not closed. So what does it mean for E not to be closed? It means it doesn't contain all of its limits points. So there exists an x of naught in R, which is a limit point of E, but it won't be contained in E. Write that part down. So there exists an x naught in R, which is a limit point of E with x naught not being in E. Okay, that's what we have. Then here's the function we're going to define for, to consider. Then we define, we consider f of x equal to 1 over x minus x naught. And that's what we're defining for every x element of E. Okay. Now, what we're going to show is this guy is not bounded on E, and this will be part of part A, case 1 of part A. Okay, so here, since x naught is not in E, then x minus x naught is never 0. For all x in E. So we're not dividing by 0. Now, what I want to tell you is, so f of x is continuous on E as x minus x naught is continuous, that function, on E. And here you would just let delta, for continuity, delta will be equal to epsilon. Okay. Okay. And then, as this is x minus x naught is continuous on E, 1, which is a constant, is continuous on E. So given any epsilon, here you can just let delta be equal to 1 in this case. That would work. And what is f of x? I'm claiming if this is continuous, it is. And 1 is continuous, it is. And so f of x is the division of two continuous functions. And I'm not going to write this, but it's the division of two continuous functions where the bottom is never 0. So that's what makes f of x continuous. Okay. Now we'd like to show that this is unbounded, as I said. So let me just say, but f of x equals 1 over x minus x naught is unbounded, and here's the reason for that. So I'll put this in parentheses. So suppose, was proved by contradiction, suppose f of x is bounded. Okay, what would that mean? That would mean that there exists an m element of R with m being bigger than 0, such that the absolute value of 1 over x minus x naught is always less than m. And that's for all x element of E. Okay, so that's what we have. Well, here we're going to consider this sequence, x of n, be a sequence to converge to x naught. Since x naught is a limit point of E, we know such a sequence x of n, which I'm referring to right here, so this sequence x of n that's in E exists. If you're a limit point, there's a sequence that goes to you in the space. So, with x of n convergent to x naught, that means that there exists an n element of the natural numbers such that for all n bigger than or equal to this big N, the distance, here this absolute value, of x of n minus x will be less than 1 over m. So 1 over m is playing the role of epsilon in the definition of convergent sequence. Okay. So, what this says is that m would be less than 1 over the absolute value of x of n minus x of naught. So, that says that the absolute value of 1 over x of big N minus x of naught will be greater than m. And that's a contradiction. Okay? So that says f of x is unbounded. And that's the parenthetical proof of what I had claimed. So that proves part A of this theorem in this case, where we're saying E is bounded. Now, I'm going to jump to part C and prove all of it. So for part C, remember, for part C, what we were saying is if E was bounded, and that's what we're talking about now, then we were supposed to create a continuous function on E which is not uniformly continuous. And what my claim is here is that this f of x equal to 1 over x minus x naught is not uniformly continuous on E. Okay. And so we want to prove this. And the way we're going to prove this is we're going to say, so I guess this is a plane. And the proof of plane, so this is part C, is the following. We're going to let epsilon equal to 1, then, and delta be greater than 0. We'll consider some cases. Case 1, suppose delta, all we know is it's bigger than 0. Suppose it's bigger than 4. All right, so here's what we do. We choose x sub 1, element of E, x sub 1 element of E, such that the distance between x sub 1 and x sub 0 is less than delta over 4. Okay. I've made a mistake in the case here. We're going to suppose delta is less than 4. Let's change that. Okay. So we're going to choose that x sub 1. Now, choose x sub 2 element of E such that if the distance between x sub 2 and x sub 0, right over here, the distance between x sub 2 and x sub 0 is less than 1/2 whatever the distance is between x sub 1 and x sub 0. How do I know that these x sub 1s and x sub 2s exist in E? It's based on x sub 0 being a limit point of E. All right. Then we look at the distance between x sub 1 and x sub 2. Well, by the definition of property of a metric, that's less than the distance between x sub 1 and x sub 0 plus the distance between x sub 0 and x sub 2. This x sub 1 was chosen so that that distance is less than, I think, delta over 4. Plus, this is 1/2 delta over 4, so that's delta over 8. Well, that's definitely less than delta. Okay, so definitely less than delta. Now, the distance between, I should say, f of x sub 1 and f of x sub 2. Now, remember, we're working in R, so when we say this distance, we mean the usual norm, the absolute value, and the difference between the points inside absolute values. Okay, so that's 1 over x sub 1 minus x sub 0 minus 1 over x sub 2 minus x sub 0. Okay, now that is going to be greater than or equal to the difference between the absolute values of each one of these parts okay, and that's going to be equal to the absolute value, 1 over the absolute value of x sub 1 minus x sub 0 minus 1 over the absolute value of x sub 2 minus x sub 0. So this quantity is bigger than that. Now, we should observe, note, that x of 2 minus x of 0 inside absolute values is 1/2, it's less than 1/2 the distance between x of 1 minus x of 0. And that's true because that's the way we chose x of 2, dealing with the distances. So, just working with this inequality, we have 1 over the absolute value of x of 1 minus x of 0 is going to be less than 1/2, and in the bottom, the absolute value of x of 2 minus x of 0, which is, of course, less than 1 over the absolute value of x of 2 minus x of 0. So, the distance between f of x of 1 and f of x of 2, which we know to be greater than or equal to by our work on that right side board, 1 over x of 2 minus, well, using the fact that 1 over x of 2 minus x of 0 inside absolute values is bigger than this, let me just write this down. This part was bigger than or equal to this. This is what's written on the whiteboard. I know that this is the bigger quantity between these two, and so that makes this a minus number. So the answer to the absolute value of this is minus this number. So that's going to be equal to 1 over x of 2 minus x of 0, inside absolute values in the bottom, okay, minus 1 over x of 1 minus x of 0 in the bottom. And that is going to be bigger than 1 over the absolute value of x of 2 minus x of 0. And let's take away something less than 1 over the absolute value of x of 1 minus x of 0. Let's take away just half of that. Okay. And so, I'm sorry, half of x of 2 minus x of 0, okay? So, I'm sorry, I'm taking away something more here. So, this part is bigger than what I'm taking away here. And so that's how come this one is, the left hand is bigger overall. So I'm taking away more. How do I know I'm taking away more? Because of this line right here. And that's equal to, so this is 1/2 absolute value of x of 2 minus x of 0. So that's where we are. Okay. Now, since the absolute value of x of 2 minus x of 0 is less than 1/2 the absolute value of x of 1 minus x of 0 in absolute values, which we know to be less than 1/2 delta over, I think we said 4 here. Then we have that the distance between x of 2 and x of 0 will be less than delta over 8. So that says that 8 over delta is going to be less than 1 over the absolute value of x of 2 minus x of 0. You can get this immediately by dividing everything by dividing everything by absolute value of x of 2 minus x of 0. So that's in the bottom over here. And then dividing everything by delta over 8. This is the inequality we get. This should be absolute values. So what that gives us is that 4 over delta is going to be less than 1 over 2 times absolute value of x of 2 minus x of 9. So that says that the distance between f of x of 1 and f of x of 2 will be greater than 4 over delta, which has got to be greater than 1. We were assuming here that delta was less than 4. Okay, give me 1 second. That's right. 1 more second. I just want to look to make sure I hadn't written anything incorrectly. So what we had was this guy was bigger than this guy. And so that makes it bigger than this guy. That's right. Good. That's just verifying. Okay, now, the other situation here is if delta, this is case 2, if delta is bigger than or equal to 4, then choose x of 1 element of v such that the distance between x of 1 and x of 0 is less than 1/4, and x of 2 element of v such that the distance between x of 2 and x of 0 is less than 1/2 delta. I'm sorry, the distance between x of 1 and x of 0. And then if you do all the previous work we did for case 1, same type of work, here's what you end up with. You end up with that the distance between x of 1 and x of 2 will be less than 1, which will be less than delta, and the distance between f of x of 1 and f of x of 2 will be greater than 4, which is greater than 1. Okay, that's our epsilon there. 1 was. And so, in all cases, we find that we can find points x of 1 and x of 2 such that no matter what delta you gave me, they were within delta units of each other, but their output values are not within 1 units of each other. So what that says is that f of x equaling 1 over x minus x naught is not uniformly continuous. And that ends the proof of claim. which is part B of the theorem. Okay, and we have done part of part A in the case where E is bounded. We want to do next part, I'm sorry, this is part C here, I should say. Part C. We next want to do the case for part B where E is bounded. We're still in the case where E is bounded. This is for part B. And we're under the case where E is bounded. So we're still thinking E is bounded. Okay, now, what are we trying to do? We're trying to come up with a function that is continuous and bounded, but it doesn't attain its maximum. Okay? That's what we're trying to do. So here's what we do. We consider g of x to be equal to 1 over 1 plus x minus x naught b squared. The x minus x naught is b squared. And then here's what I can tell you. Then G is continuous. On E, and because the quantity x minus x naught is continuous, we talked about that. It's continuous, so if you square it, you're multiplying it by itself. So I multiply it by itself. So if you take two continuous functions and multiply them together, you get a continuous function. So this is continuous. And then, what else did we have? If we add 1 to it, that's continuous. And the reason is the addition of two continuous functions is continuous. Okay. And then lastly, I'll say as 1 is continuous. We've shown that. Okay. And lastly, g of x is equal to the division of two continuous functions where the bottom is never 0. Is the division of two continuous functions. With the bottom never being 0, with the denominator never being 0. Okay, that's good. Okay. Now, let's look at that bottom just a little bit more. So note, x minus x naught squared. Well, look, in this case, x naught was chosen. Don't forget about our x naught. It's a limit point of E which is not an E, okay? Because E is not closed in this case, with E being bounded. And so this guy is never 0. And if it's never 0, it's got to be greater than 0. And that's true for all x in E. Again, as x has got to be different than x naught. Then that says that 1 plus x minus x naught to b squared is going to be greater than 1. So that says that 1, if we divide everything by 1 plus the quantity x minus x naught to be squared, that's going to be greater than 1 over 1 plus x minus x naught to b squared, which has got to be greater than 0 for all x. Okay, so that means our g of x is bounded. Okay, so in this case of E being bounded, we've produced a function, g of x, which is bounded and continuous on E. Okay, well, the next thing we want to do is show that it doesn't achieve its maximum, its supreme. Okay. Well, the first thing I want us to do is figure out what is the supremum for the output values. If I look at the collection of output values. Well, I'll say it. Note that the supremum of all the output values, g of x, that's x is in E, that is equal to 1, as definitely it's clear 1 is an upper bound. We've already showed that. GB. And for all u less than 1, okay, so if you give me something less than what we think 1 is the supremum. If you give me something less than it to prove that 1 is the supremum, then it cannot be an upper bound, okay? Because this is the least of the upper bound. So if you give me something less than it, it cannot be an upper bound. Let's show that. This would say that 1 minus u is greater than 0. And that would say that 1 minus u over u will be greater than 0. Okay? Here I'm thinking that u has to be greater than 0. Okay? If you give me something that's equal to 0 or less than 0, we know that it's not an upper bound. Okay? So the square root of 1 minus u over u is going to be greater than 0. And now we look at it. So since x is sub naught is a limit point of E, then there exists an x sub 1 element D such that the absolute value of x sub 1 minus x sub naught will be less than this quantity here, 1 minus u over u. You think of that as the radius of the neighborhood. Okay, so working with that, we have that x sub 1 minus x sub naught to b squared, square root of that, that's what that guy is, So just this guy to b squared is going to be less than that guy squared over there, which is 1 minus u over u. So we get that u times x1 minus x naught to b squared is less than 1 minus u. So that tells us, working with what we just had written, that we have u plus u times x1 minus x naught to b squared is less than 1. So that says, factoring out u, that u times 1 plus x of 1 minus x of naught to b squared is less than 1. So that says that u is less than 1 over 1 plus x of 1 minus x of naught. Oops, this should need parentheses here. To b squared. Okay. And so that says that u, so there exists an x1, such that g of that x1 is bigger than u. So that says u can't be an upper bound. It's not an upper bound of g. Let me look at something for a second. Yeah, that's what I should say. Thus, 1 is the supreme of all the x's in E of g of x. And g of x is always less than 1. We've shown that. Thus, g has no maximum. In E. Okay. Now, we haven't got that much further to go. What we're going to do is look at case 2, and that's based on E. And so case 2 is going to deal with E not being bounded. So let me write that up. So suppose E is not bounded. Okay? All right, we need to prove parts A and B here. And part A was we were going to show that there was some continuous function that's not bounded on E. And so here, for part A, this is case 2. F of x equaling to x is a function on E that is not bounded, as E is not bounded. This ends the proof for part A. That is, in all cases, we have produced all cases for E, we've produced a function that is that is continuous. Okay? Okay? and not bounded. I guess I should say, as a continuous function. Only if it is not bounded. Okay, so we've done part A. Now for part B, in this last case that we need to consider, okay, with E being not bounded, consider this function. H of x is equal to x squared over 1 plus x squared. That's for every x in E. Okay. Very quickly, let's make a simple observation. 0 is less than 1. So that says that 0 is less than or equal to x squared, which is less than 1 plus x squared. So we're doing work like we did before with that function g of x. So 0 is less than or equal to x squared, which is less than, I'm sorry, x squared over 1 plus x squared, what we get, which is going to be less than 1. Okay. So here's what we have. We're summarizing this. So 0 is less than or equal to h of x, which is less than or equal to 1. So this means that less than 1, I should say. So h of x is bounded. Now, again, just let me say this without having to write it all down, but h of x is continuous. Okay, I'm not going to put in the details again, but x is continuous, x times x is continuous, x times x is continuous. 1 is continuous. You add 2 continuous functions, you get a continuous function. Divide a continuous function, you get a continuous function, as long as the bottom's never 0, and that's not ever 0. Okay, so that's what we have. Okay, that's good. All right, and then very similarly, if we let u be less than or equal to 1, but greater than 0. So it doesn't matter. If u is less than 0, we know that it can't be an upper bound. Okay, we know that. And if we just let, since x is non-zero, here when I this quantity can never be 0. I should make this change here. Okay. This guy can never be 0. Well, it could be 0 if x equals 0, so I guess we could have 0. E is unbounded. Since E is unbounded, I guess I should say it has to contain more than 0. So there's got to be something in here that's bigger than 0. So 0 cannot be a lower bound. Okay, and then if you give me anything greater than 0, 21. And we know 1 is an upper bound, okay? Then 1 minus u, again, is going to be greater than 0. So there exists an m element of J such that u is less than m times 1 minus u. This is from an early result in part in chapter 1, I should say. So since E is unbounded, there exists an x of 2 that's bigger than 1, that's in E, such that x of 2 has to be bigger than m. Maybe it should be the absolute value of x of 2. Okay. So that's going to give us x of 2 squared is going to be bigger than m. So what we have, we're almost done. So there exists an x of 2 in E such that u is less than x of 2 squared times 1 minus u. So u is going to be less than x of 2 squared minus x of 2 squared times u. So u plus u times x of 2 squared will be less than x of 2 squared. So that says that u times 1 plus x of 2 squared is going to be less than x of 2 to be squared. So that says that u is less than 1 plus x of 2 squared over 2. And not over 2, but over x of 2 squared. Thus, u is not an upper bound. For h of e. Okay. Thus, 1 is equal to the sup over all x in E of h of x and h of x never attains 1. And so that ends the proof for part C for this case, in all cases. And that ends this theorem. And that ends this lecture. Thank you very much for your patience.